So last week we talked about this idea of a balanced chemical. Talked about this idea of taking a chemical reaction and generating a series of chemical reactions associated with this, such that we divide each of these reactions up into their respective components, where one of these would be a reduction, visual pun, and another one would be an oxidation, and a resulting electron transfer that takes place, which we would have to then balance out. To make this process work. So there's a series of what we call half reactions associated with this. So we could conceptually break this iron up into an iron reacting with iron plus 2 electrons, and then the H2 undergoing the reduction, or the oxidation, excuse me. And when we combine those two half reactions, we can combine them together to get the balanced chemical reaction. And we looked at these balanced under under acidic and basic conditions. We're not going to go through that right now. Now, so this is a series of chemical reactions that takes place. Now the question is, or not the question, the statement is, you do not have to have these two chemical reactions take place in the same location. If you can somehow trick the system into undergoing each of these chemical reactions, to the universe's knowledge, they are going to progress. All we care about for a reaction to be spontaneous is that it has, again, that negative delta G, that negative Gibbs free energy. All right. So there's a tendency for these reactions to take place, a natural tendency for these reactions to take place. So if they take place, they take place. It shouldn't matter whether they're taking place together or separated from each other by a continent, though in practical terms it does matter. So this is the heart of electrochemistry. Looking at how chemical reactions can be used to generate electricity, and in particular the electric potential associated with chemical reactions, E. Often called EMF, or just plain old voltage. Now, we've heard many of these processes. We've all heard of voltage. What that really is, it turns out that potential, in many ways, is very similar to gravity. If you've paid attention in physics, you know that the force on an object, gravitationally, is related to its mass and the distance between the two objects. And so there's a force that's of attraction. More importantly, like I said, there's a force of attraction between these objects that depends on their mass and how far they are apart from one another. And so if you have an object, and if you lift that object through this force area, we're doing work. Work is equal to force times distance. All right. So by lifting this object against this gravity well, we are doing work on the object. And that change in height translates to a certain amount of energy expended. Well, we've talked about chemical reactions and their ability to do work or release heat. And so we can also think about another type of work, and that's something that takes place between objects of opposite charge. If you have two objects of opposite charge, there's going to be a force of attraction between them, and you separate them by some sort of distance. Separate them by some distance. The act of pulling these two charges apart involves work. Taking two materials that are attracted to one another and pulling them apart requires work to be done. Right? So that is also a type of work. It turns out that the force associated with electrical interactions is a little more complex, but effectively the same. Where we deal with, rather than the masses, we deal with the charge on the objects. And the attraction between them, again, is another constant that we don't have to worry a deal of it. But effectively, these two forces have the same basic form. So we can think of the ability to push charges around in a force with some sort of force is what we call is a form of energy. It's a form of work. That act of moving a charges around. So anything that can move a charge around, we call potential. So that's potential. So it turns out we can relate the potential voltage, often given the symbol E. So how does voltage manifest itself? So the potential is the force per unit charge that is being moved through that. So the E, the voltage, turns out that the units are typically volts. 1 volt would be equal to the amount of force of 1 joule applied to 1 coulomb of charge. Now, a coulomb is a way of counting, is the basic unit of charge. It turns out that we can define a coulomb in terms of the Faraday constant, F. Turns out that the Faraday constant is equal to 9.647 times 10 to the 4th coulombs per mole of electrons. If you had 1 mole of electrons, it would have 9.64 times 10 to the 4th coulombs of charge associated with it. So, by moving that many that many coulombs of charge through a potential of 1 volt, it would be considered, it would take 1 joule of energy. Now, it turns out that sometimes it's more useful for us to think about it in terms of another definition, is that a more useful one, is that 1 joule would equal 1 coulomb times 1 volt. 1 coulomb delivered at 1 volt would take a joule of energy. So what this allows us to do is relate number of charge carriers and the potential to how much energy is released or transferred in a chemical reaction. Do you remember when we were balancing chemical reactions a couple electronic minutes ago? One of the things I said is that we have to be aware of how many electrons are being transferred. The reason we care is this. This allows us to relate energy, joules, to potential, how much work could potentially be done. Now it turns out that the work that can be done is equal to negative NFE, where this is again Faraday's constant. E is the potential, and N happens to be the moles of electrons transferred. Well, we've actually seen this work show up. It turns out that the maximum work, the maximum energy that you can get out of a system is delta G. All right? So delta G of a chemical reaction is equal to negative NFE. Now there's some consequences of this. Right? Negative delta G's correspond to positive potentials. All right. So when a reaction has a positive potential, that means that it is spontaneous. When a reaction is non-spontaneous, that means it has a negative potential. Of course, it's just the long-running habit of chemistry's messing with you. All right. So this potential, all right, for a given chemical reaction can be measured. A reaction that is spontaneous naturally wants to give up its electrons, and so we can harness this potential energy and measure the relative potential energy between these, the relative potential between each of these chemical reactions. Okay? And this is where we bring in the concept of cell potential and standard reduction potential. Standard reduction potentials. So a standard reduction potential, it turns out that potential is relative. I mean, the potential, like gravitational force, it depends on where you start, how high you are compared to how low you are. But, so we can sort of set a base sea level, how set a base sea level. And so we've defined the 0 point, the chemical reaction that has zero potential, as the following. Hydrogen gas going to 2H plus 2 electrons. As having a potential equal to 0 volts. Now what that means is that the reverse reaction also has a potential of 0 volts as well. Now what we can do is then we can compare a chemical reaction to this one and measure its potential. In fact, how do you do this? You actually set this up. You have a reaction that's set up in the presence of hydrogen gas going to hydrogen ions, the hydronium ion in water at 1 molar concentration and 1 atmosphere of pressure, and you can measure the the concentrations, you can measure the reduction potential, the relative stability of the products compared to this. And you can report how readily a compound is undergoing reduction. So let's just take a look at a table. So here we have hydrogen plus 2 electrons going to H2 gas with a 0 voltage. How readily something else is reduced or oxidized compared to that represents their individual reduction potential. The higher the voltage, the higher the cell potential, the more likely that reaction will take place. The more likely it will take place. So let's take a look at an example. Bromine plus 2 electrons to produce the bromine ion. The bromine is undergoing reduction to form bromide, has a cell potential of 1 volt approximately, compared to hydrogen. This means that the reaction takes place much more readily. Now, we have these half reactions that we talked about in previous slides. An iron being reduced to iron oxide, iron being reduced to solid iron, and hydrogen being oxidized to hydrogen plus 2. And we can look at what the cell potential of each of these reactions is. It turns out that, unlike delta G's, it's out that like gives free energy. When you reverse a reaction, that leads to a change in the sign of the potential. All right? But unlike delta G, when you double the reaction, or when you change the stoichiometry, there's no change in the potential. Because potential is related to potential per unit charge. It's a quantity that takes into account the energy per unit charge. So that means that it's sort of quantity independent. The voltage can be quantity independent because it's per unit charge. In short, that Faraday's constant and the taking care of the number of electrons alters how we handle it. So we can use it pretty much the same way we use delta G. We can build reactions and combine chemical quantities in a similar fashion. So let's take a look at one of the first chemical reactions that was discovered electrochemically. And this is the one we've done in the lab, and that's copper ions, plus 2, plus solid zinc goes to copper metal, plus zinc ions. Now, we can look up each of these half reactions, copper plus 2, plus 2 electrons goes to copper 0, and zinc goes to zinc plus 2 electrons. Now this isn't actually a worthless exercise that we just did, where this would be the reduction, this would be the oxidation. When we go back to our, this wasn't, like I said, a worthless exercise. It turns out that we need this information, because then once we see these half reactions, we can then take the half reactions and look at the chart, and we see these half reactions where we have copper plus 2 going to copper 0. Here we go. Copper plus 2 electrons goes to copper 0, has a cell potential. We're just going to call this E red is equal to 0.34 volts. And the E-ox, if we take a look at the oxidation that's taking place, well, these are all reduction potentials. So where do we find the oxidation? Well, we have this zinc undergoing oxidation. A reduction in this case, well, we can just flip the reaction. Would be equal to, rather than negative 76, it would be 0.76. Now, some books do something a little bit different, and some of them have you. In our case, this is what we're doing. In our case, we're just taking the E for the reduction and we're adding it to the E for the oxidation, where we have corrected the sign. We've reversed the reaction, and we then combine them in the same fashion. This would be 1.10 volts would be the cell potential. Now, since these are all recorded under standard state conditions, we would call this E naught. Right. Now, some books, E red minus E ox, right, where this is the uncorrected version. So just be cautious. Be consistent. We're not going to use this one. We're going to instead focus on this one as our go for this method. Why? Because it has a nice synergy with has a nice synergy with the other. So this is how we find the cell potential. We'll come back to this in the next talk. We'll start using this more effectively in the next, but I'll just run through some examples and talk about the idiosyncrasies. So cell potential is another way of expressing whether a reaction is spontaneous or not. As we can tell from this voltage, this reaction is spontaneous. Positive cell potential is equal to spontaneous. All right. We would say that this would have a positive voltage. What's really funny is if you reverse this reaction, if you were to get a negative voltage, the reaction would preferentially run the other way. All right, we'll talk about that more in the next